Good morning, good afternoon. Thank you for joining us, everyone. I want to just kick off our fantastic event here with the University of Waterloo and my friend Lenoy, who is going to be showing you how he uses Tableau and Python to better predict student enrollment. So I'm really, really excited about this. I can't think of two more popular topics right now. So most of you know me, some of you don't. My name is Erica Dale. I am a senior account manager at Newcomps. That's code for I'm old and I've been doing this a very long time. I actually prefer analytics evangelist because what I do is I get out my soapbox and I stand on it and I preach and I tell you all what to do with your data. And Lenoy is the manager of data and analytics and reporting at University of Waterloo. He's one of the guys that actually does all this good stuff. So I'm super excited to see his presentation today. I'm going to go really, really fast just because Lenoy's presentation is very full and action-packed. So please feel free to ask questions as we go. There's a questions and a chat function in the bottom part of the widget for GoToWebinar. I'll moderate and interrupt Lenoy because that's what I do. I interrupt people. And we will try and keep things moving and get all your questions answered as we go. We're proud to be presenting this on behalf of the higher education analytics community. This community, for those of you who are not aware, is a consortium of Newcomp, IBM, and three of our cornerstone partners, the founding partners, Laurier, Waterloo, and Conestoga. So we're very proud to be working with them to bring you good quality content about analytics and data in your industry. Always happy to hear your suggestions, your requests. If you have something cool you want to show, we would love to see it. A little bit about Newcomp. This is our one and only, well, maybe two and only shameless plug slide. We are an analytics focused business partner and implementer based out of Toronto, but we service continental North America. That includes the Caribbean. I did not get that territory, unfortunately, but I got St. John's and Winnipeg, so that's super cool. These are a few of our key partners. We are happy to be at the highest level of partnership with Tableau, Microsoft, IBM, Alteryx. We've got great partnerships going with Snowflake Data Robot, and ThoughtSpot, to name a few, but there are a few missing from this slide as well. So please, if you have any questions at all about what to do with your data once you've stored it, we're happy to help you. A little bit about the services that we provide, what's in our DNA. We literally grew up in this space. We started out, of course, in BI, data visualization, helping people that develop effective ways of looking at the data to drive a user to action. One of the cornerstones is financial planning and analytics, doing what if scenario modeling. What if we have a double cohort because of COVID? What if we have a difference in the way the grants are funded? These types of things all need a data and analytics tool to drive them. Of course, the AI and machine learning, we wouldn't be an analytics company if we didn't do that. So we can help you deploy or get your first POC into AI and machine learning. Data management and governance, well, we all know that that is the foundation the house is built on. If we don't have good data and good processes, we can't effectively monitor and measure them, plan from them, or teach a tool to use. All of this is done with our vendor partners or open source analytics as you choose. We cover everything from advisory, vision setting, roadmaps, that type of thing, right on through to development, planning. We can do managed analytics where we become your de facto analytic department, and right on into training and mentoring, which to me is the most important part of your project. The more enabled your users are as we go along, the better adopted the technology will be. So really with that, now I pressed the wrong button, Alex. Really with that, we want to hand this over to Lenoy from University of Waterloo. Lenoy, thank you so much for joining us again. I love your presentation. I'm so pleased you agreed to share it with the rest of the community.
Okay, so thank you, Erica. Just want to confirm that you can see the first slide of the presentation.
We certainly can. We're alive and well.
Okay, so here we go. Okay, thank you, and good afternoon, everyone, wherever you might be joining from, or good morning. So I will be discussing a prototype enrollment forecasting model currently being tested by Institutional Analysis and Planning at the University of Waterloo. There's quite a bit to get through here. The first time I did this presentation, it took over an hour and a half, so I'm going to do my best to get through the main slides in about 30 or 45 minutes to give time for questions at the end. And on this first page, you can see my new favorite quote, "All models are wrong, but some are useful," from George Box, which just reminds us that we are not necessarily looking for perfection here, but for something that can be used for planning at the highest levels and perhaps at the mid levels of the institution. So let's get started. Okay, so this is the agenda for today. I'll start by giving some basic facts about the University of Waterloo and IAP, Institutional Analysis and Planning, that create forecasting challenges in our environment. Then I'll talk about the scope of the project as well. Next, I'll describe the current model at a high level and some of the challenges we have with the current model. Then I'll discuss the goals of the prototype, the project. Next, I'll introduce you to some terms and values that you will see as I do a demo. So that's the data dictionary. Next, I'll do a quick refresher on the Markov model and how it's implemented using linear algebra. And then I'll show the algorithm that's used for forecasting future enrollments. I'll then talk about the design of the model. There's 6 components to it. And next, I'll step you through the 6 components, steps 1 through 6. And in the middle there, I'll do a couple brief demos just to show you what it actually looks like in practice. I'll finish up with Q&A. Any questions you might have specific questions about certain slides. And if time allows, there are some additional slides that you might find interesting that I will share with you. But if we don't get time to go through the slides at the very end under PS, I'll send you a copy of the presentation anyway, and you can read the notes. Okay. So the University of Waterloo, of course, is best known for the co-op programs. It's the largest co-op program in the world. More than half of the programs are co-op with varied academic and work streams. That means, of course, that mapping student enrollment is complicated because you have students moving between academic and work terms on campus, off campus, continually for 4 years. The university is open year-round. So that means many students take advantage of the option of taking extra courses when they're on a work term, or perhaps they're regular students, meaning not co-op students, who would typically be off for the summer term, the spring term, and they may take courses over that term to finish their program early, or if they want to get an additional minor, they may choose to do that as well. Also, we have 22% of our student population is international. And I believe it's the 2nd largest in the province in Ontario after U of T. Now, in general, international students behave differently from domestic students in terms of how they flow through the university. And of course, the higher international fees mean that as far as tuition is concerned, they're going to contribute more than 22% to the bottom line. So these are some of the unique challenges we have with enrollment forecasting. Talking about institutional analysis and planning, that's the IR department, IR shop at Waterloo. It has significant responsibilities, but for the purposes of our presentation today, I'm just going to highlight revenue projection. And there are 3 main sources of revenue for the institution: grant revenue, tuition revenue, and co-op fees, because since more than half the campus is co-op and the students pay co-op fees in the academic term just prior to any work terms they may have, that's a significant source of revenue as well. So if you think about those 3 sources, grant revenue, tuition revenue, and co-op fees, it means then that when we're doing enrollment projections, the measures that are important are WGU, weighted grant unit, FTE, full-time equivalent, and of course, headcount. And we have to keep track of all 3 of those. So over in the 2nd column, just talking about the scope of the project. So in terms of forecasting, we're not concerned with first-year uptake. In other words, how many applicants end up enrolling, nor are we concerned with whether students who actually enrolled actually ended up paying fees and coming on campus. we're totally focused for this prototype on students from their registrations in their first semester, first year, until they graduate. In terms of study level, grad forecasting is significantly less complex than undergrad, so we're not going to include grad students. We're just going to deal with the undergrad students. And then we're going to include all academic plans. That is 3-year degrees, 4-year degrees, as well as non-degree students. Okay. So the current model, the original application was built in the 1970s before our current student system, PeopleSoft Campus Solutions, colloquially known as Quest, was implemented. There's an Oracle database on the back end, Microsoft Access on the front end for forms and reports, and then Visual Basic for applications is where all the code resides. Because it was implemented so many decades ago, it uses older terminology. And so that sometimes makes it difficult to communicate and to share information with our partners and our clients across campus, because the terminology that's in the application is not necessarily what they're used to in their day-to-day jobs. It uses the cohort survival model, and it meaning that what percentage of students in any given forecast group continue on to subsequent semesters. So do 93% go from year 1 to year 2? Do 97% go from year 1 to year 4? That's what I mean by cohort survival. And we have about 3,000 forecast lines, what the current model calls forecast groups. And those 4,000 forecast lines are made up of 12 different components. It's a little bit out of date, and most of the forecast lines are empty, meaning they're not contributing anything to the forecast, but they still have to be maintained. Full-time equivalent is predicted, and then we calculate factors, what we call factors, to convert to measures like headcount and WGU. And it's really an institutional level forecast, right? We, in IAP, we answer to the provost and executive council at the university. And so the forecast was really built to serve the executive level of the institution. It's not as useful for doing faculty level forecasting and levels lower than that. And last but not least, it uses faculty targets. So when we're pulling in intakes from the various forecast groups, those intakes are coming in from faculty targets as opposed to targets that might be estimated, for example, using linear regression. Anyway, in terms of pressures to change the current model, bug fixes, obviously, because the program has to be updated frequently with university changes, with departmental changes. Number two, some years ago, Waterloo introduced a new revenue sharing and cost sharing model called the Waterloo budget model. And that model really brought some of the limitations of the current forecast into sharp focus, as you might imagine. Number three, SMA2 and SMA3, the Ontario government strategic mandate agreements, which suggested changes in the way grant revenue would be dispensed, also suggested that we needed to change the way we do enrollment forecasting. And of course, there were new requests from the Provost's Office for long-term strategic planning, as well as requests for more detailed information from the various faculties and departments. And finally, the big data revolution, I'm sure you're all familiar with it, suggested that the current way of forecasting could be significantly improved. So that's really the current model and the pressures to change it. So the current forecast is trusted, and of course it's been in use, as I've said, for decades. So we had to set really lofty goals for the prototype. So accurate. We're measuring fiscal FTE because we're comparing it against the current forecast, even though we are hoping to produce WGUs and headcounts as well. 5% is really the threshold. Really, the gold standard is 3. But we're looking at a 3-year horizon. We don't have to plan beyond 3 years. So let's say within 5% over 3 years. That's what we're aiming for from an accuracy perspective. In terms of flexible, because of the varied stakeholders on campus, I've mentioned before that some people want to see WGUs, some want to see FTEs, some want to see headcounts, but not just in terms of measures. Depending on the department you're talking to, academic year matters. Other departments, it's fiscal years. Others, it's calendar year. So time periods, we have to be flexible in that. Levels of detail is kind of self-explanatory, faculties or departments. And of course, we want to be flexible in terms of allowing overrides and adjustments to the forecast, because of course, forecasting is an art and a science. Moving on to complete, we want to be able to forecast academic enrollments, meaning enrollments on academic terms, but also enrollments on work terms. When students are on a co-op term, we want to be able to track those as well. Degree and non-degree students, I mentioned before, and also first year and upper year entry programs. So your first year program is your typical program, arts, French, engineering, health studies, but upper year programs like pharmacy, optometry, social work, where you need a first degree to start, we want to track those as well. And last but not least, we want the prototype to be user-friendly, to use a common language that the university campus understands. We want to, of course, implement security and privacy controls using our Nexus security groups. And we want to do web reporting and editing as opposed to sending, PDF and Excel attachments over email, right? So we want to enable that. So let's talk a little bit about the data dictionary. Here are some of the terms and values that you're going to see as I do examples. First column, student term or S term. It's how we denote semesters. The first character is the century, so 1 represents 2000 and above, 21st century. The next 2 characters are the year, so 17, 18, 19, 2017, 2018, 2019. The last character is the first month of the semester. So 9 for September, 1 for January, and 5 for May, since we're open year round. So the text that's colored in red represents the calendar year. There's 3 semesters in calendar year 2018, 1181 through 1189. And the first 3 are, of course, the academic year, 1179, academic year 2017-2018, September 2017 through May 2018. That's how we denote the semesters. The year level is the term of study the student registers in. 1A is the first semester or first year. 1A-WT is a student who just completed 1A and is on a work term. 1B, second academic semester of first year, so on and so forth, through to 4A, 4B. NL stands for no level, usually for students taking 1 or 2 courses, usually international students who are just getting acclimated to Canada. Perhaps English isn't their first language, so they take a reduced course load. Progression. When we forecast students, the total projected for any given program in any given semester is a combination of students who are new to the university, intakes, continuing students, meaning students who perhaps started their first year, didn't do so well, take a couple semesters off, come back again the following fall, let's say, 12 months later. Transfer students. In this case, we're not talking about students who might have transferred in from a college or a university. We're talking about students who switch programs, so engineering to science or math to arts. And then M04, M08, and M012 represent students who register 4 months after their last registration or 8 months after their last registration. Maybe an example will make more sense. If I'm registered this fall, in this fall semester, and I'm also registered again next in the winter in January, I would be an M04 student. But if I have the summer off, and then between January of next year, I take the summer off and I'm back in the fall, I would be categorized as M08. So 8 months between registrations. And then there's M12. Usually those are continuing students, took a year off, came back. And last but not least, the forecast group. So there was a bit of back and forth on this, but really what it is we group our students by a combination of the faculty they're in, the program that they're taking, whether they're doing a 4-year honors program or a 3-year general program, that's for grants, whether they're doing a co-op program or a regular program. That impacts the tuition fee that you're charged. And of course, the fee schedule, whether you're Canadian or international, is on the end. So reading from top to bottom, section 1, applied health studies, arts, engineering, environment, math, kinesiology, East Asian studies, French, electrical engineering, geography and aviation, computer science, and then the rest you can figure out. So these are the forecast groups we have. About 450, 480 right now with this categorization. That's the data dictionary. All right, hopefully I'm not going too quickly. All right, let's talk about the Markov model linear algebra. I'm sure most of you are familiar with it. It's been around for many, many decades. The Markov model is a cohort survival algorithm, usually implemented with linear algebra. Here are two simple examples. The matrix in the middle represents the cohort survival or transition rates. In the first example, we assume we know the transition rates between year 1, year 2, year 3, year 4, meaning you start here, this is your start, this is your end. And so if you read the first row as an example, if you're a student in year 1, according to this transition matrix, 1%, 1 in every 100, will repeat year 1, 93 in every 100 will repeat year 2, so on and so forth. The total does not add up to 100. The assumption is that 6% of the students are going to withdraw or drop out. And so that's the transition matrix for years 1 through year 4. Note the diagonal line in red font. These are students who repeat their year level. So 1%, 2%, 1%, 5%. And note that every number below the diagonal is 0, meaning no student moves down a level. No one moves from year 2 to year 1 or from year 3 to year 1 or year 2. Okay, in the second example, and I should say, if you do the matrix multiplication, this is very easy to do in Excel. If you've got 1,000 students in each year level and you do the matrix multiplication, you end up with 10 students in year 1, those are the repeaters, 950 students in year 2, so on and so forth. Down below, we have a second example. It's a little bit more detailed. We're not doing years anymore, we're doing semesters. And here it's assumed that we know the transition rates between fall, winter, spring in a given year for a single cohort of students. Note the diagonal lines, this time they're all zeros, and that's because you can't repeat a semester in any given year. You can't repeat fall term in a certain year. But the principle is the same. 95% of students move from fall to winter. And if you do the matrix multiplication, 100 fall students will move to, in the winter term, to be 95 students. The assumption is 5 students or 5% of students do not continue on. So very basic, and I'm sure most of you are familiar with it. So notice that as you apply the matrix, you're moving students through the various year levels or semesters, meaning you have to, the algorithm requires you to, at some point, put in intakes for future semesters. So that's the Markov model, basically. This is the transition matrix that we're using from the prototype. We're not using a transition matrix based on years. We're not using one based on semesters. We're using one based on year levels. So down for the starting year levels, you can see them down here, 1A work term, 1B work term, all the way through. And then the ending across the top, 1A work term, 1B work term, so on and so forth. So we're using year levels in the transition matrix. And this example is for mechanical engineering students in the Faculty of Engineering, and they're Canadian students, and we're moving them from fall to winter. Again, it's really simple. If you take the time and you just read it across, if for students who are in 1A in the fall in mechanical engineering, historically, 52% of them move on to a work term immediately after 1A, 48% of them move on to 1B, meaning a second academic semester. And I've removed all the zeros from the matrix to make it easier to read, but it should be fairly straightforward. This is the this is our transition matrix, or a sample of it in the prototype. So if you think that we've got 480 forecast groups, and if you think of all the different transitions between semesters, you can quickly see that we get between, say, 480, maybe 10 different transitions. You're ending up between 4,000 and 5,000 matrices. So although technically you could do this prototype in Excel, once you get into these high numbers, 4,000, 5,000, obviously you're going to switch from using Excel and using code instead, and that's where we implemented Python. Okay, next slide. A bit like drinking from a fire hose, I apologize. So this is the algorithm. So what does the complete formula looks like? The complete formula requires applying the correct transitions in turn for as many periods into the future as you require. In our case, we're only being asked to forecast 3 years into the future. So for any given forecast group, take the enrollment at time t that's known, say fall of 2021, multiply it by the known transition, so fall to winter, from t to t+1, you do that matrix multiplication as per the Markov model, you're going to end up with a projected number for the winter term. But you also have to take into account any students, any new students that may come in the winter term intakes, and also any transfers that may show up in this forecast group coming from another forecast group. And so those would be transfers. You do that multiplication, add those two, you get enrollment in the winter term, enrollment at time t+1. If you take the t+1 numbers and you multiply it by a transition, the unknown transition from t+1 to t+2, then you add the intakes at t+2 and the transfers at t+2, you get the enrollment at times t+2. So very straightforward. And of course, if you repeat this enough times, in this case, I'm repeating it 15 times, you end up with 15 enrollments in the future as per the Markov model from t+1 to t+15, just by starting with the enrollment at time t. Now, what we find is very helpful with this algorithm is that it allows us, within reason, to make adjustments to either the transitions or the intakes or the transfers for any given future period. And that allows you a very fine degree of control on the forecast. So the analogy that I've sometimes used in describing it to partners on campuses, it's like a car with a manual transmission versus an automatic transmission. You're still driving the car, but the manual transmission gives you that much greater level of control in terms of the forecasting. So that's why we are working with this model. So that's the algorithm. This is what the prototype design looks like. No need to read the slides. Just high-level overview. There's 6 components, 6 distinct components. The reason we had 6 distinct components was to allow us to enhance or improve any one of the components as needed while keeping everything else the same. And the interfaces between the components are either database tables or CSV files. And the reason that we used those interface types was to allow, it's for the art and the science, right? To allow adjustments to be made as needed if the numbers that were being produced are not what the forecasters or the analysts on campus thinks are appropriate. So what are the 6 components of the design? Number 1, enrollments. Gather all historical enrollment records, 1 per student per semester. Each enrollment for each student records course load, what program that they're in, so on and so forth. Step number 2, transitions. So calculate the matrices. So determine the transition matrices. I showed you examples before for any forecast group or for all forecast groups for fall, winter, spring, between the year levels. Number 3, predict future intakes. Really what we're doing is taking historical intakes and projecting what the intakes are likely to be per program for the next X years. Then the forecast, here's where we implement the algorithm in step 4. We take the transitions, we take the intakes, also transfers. I should have said intakes and transfers here, but we take that and we in Python, we implement that algorithm in Python to produce the forecast for the 15 semesters in the future. Then we put all the data output, all the CSV files into a multi-dimensional cube for that really allows flexible reporting, and I'll explain more after. And then at the end, we have some reports, and we use Tableau for that report. And basically, those reports are for sharing across campus. So I've highlighted two of the steps. One is the transitions, which we use, it's ETL, basically. We're using Tableau Prep for that right now. And number 6, the Tableau Reports, we use Tableau there as well. So I'm going to be demoing those two, but I just want to remind you there are 6 distinct components in the model. Oh, total runtime, everything between half a day and a day. For now, it's being run manually. We're looking into ways to automate it. So let's go through the steps. So here's component 1, student registrations. There's a lot on the screen. It's a screenshot from Tableau Prep. What I'd like to really get across here is this is essentially a data dictionary. If you're used to using Tableau Prep, it shows the different values in the database for the various fields. So here are all the values for S-term in the database, all the various programs, all the year levels. This is the interesting one. These are all the students that are listed in the database. I forget how many rows are in here, maybe 3 million. Student ID 20447455. If you click on it in Tableau Prep, it will highlight in the rows below all the records in the database associated with that one student. So here we have 13 records for that one student out of the 3 million plus rows. And what's interesting here, all the S terms that they were registered in, they started in fall of 2012, they graduated after winter of 2016. What programs they were enrolled in while they're at the university? Well, they started in biochemistry in the science faculty, and then they moved to health studies. They graduated in health studies. The various year levels they moved through, it was a co-op student. You can see that because they had work terms. What else? We talked about science versus applied health studies. They switched faculties. And then there's some measures over to right that we're going to use. And oh yeah, they're a Canadian student.
No, we do have a question that's actually quite relevant here.
Yes.
How many years of data are you using in this prototype to drive the model?
So we don't use any more than 5. But the model actually uses 5 years, 3 years, and 1 year. And the reason for that is while we're doing our testing, we recognize that some programs, the forecast is actually better if you use 1 year versus if you're using 5 years. So the model actually allows us to do 5, 3, or 1 dynamically.
That's great. Thank you. Thanks, Neil, for the great question.
Okay, yeah, great question. Yeah, the 5-year, 3-year, 1 year also matters if, for example, you have a new program. So if you have a new program like architectural engineering and it doesn't have 5 years of history, you're better off using the 1 year historical period. But great question. Okay, so how do we calculate the transitions and the transfers and the intakes? The Venn diagram is the best way to describe it. So imagine that the mustard, yellow oval are enrollments in S-term, let's call it N, let's call it a fall semester. So enrollments in S-term N, that's the student registration. The blue oval, enrollments in S-term N+1, that's the winter semester. So if students are registered in both the fall and the winter semester, those who are in the fall semester, but not in the winter semester, so over here, are either they withdrew from their program or they graduated. Moving over to the far right, if they're in the subsequent semester, but they're not in the prior semester, well, they must be new students that are coming in, or or external transfers, for example, from another university. So we group those together, intakes and external transfers, because they're new to the university. And then in the middle, if a student was registered in both semesters, either A, they're transitioning between year levels, so 1A to 1B to 2A to 2B, or they switched programs. They went from environment to science, they went from engineering to arts. Those are what we call internal transfers. So if you look at this Venn diagram here, on the right, I've highlighted that it's actually happening in section component 2 of the forecast. And here is where I think it's probably a good point to do a little bit of a demo. So I'm just gonna show you the Tableau Prep where we calculate the transitions. So here we have, oops, it did not open. Oh, there it is, it is open. So this is our Tableau Prep flow. It is quite complicated. If I zoom out, you won't be able to see much of it. But Tableau Prep is an ETL tool that we are very well versed in institutional analysis and planning. And basically, all of these icons on the screen represent steps that we follow to scrub the data and calculate transitions and intakes and transfers. So let's see if I can do like a 2 or 3 minute demo of Tableau Prep for those who aren't familiar with it. So this icon represents the database source, the source data. And if I click on it, it brings up all the details. So all the fields that are in that database. Let me make it a little bit more visible. So S terms in there, year levels in there, student IDs in there, no surprise there. If I go to the next step with Tableau Prep, you can see very similar to that screenshot I showed before. You can see that at the very top, let me see if I can show you as much data as possible. Okay, so coming right off the database, you can see that we've got all this data. How many rows here? 227,000 rows. These are all the S terms we have. And down below, you actually have the database records. So basically in Tableau Prep, there are various ETL steps that happen to transform the data. I'll move over to where we calculate the transitions. Actually, maybe I should do this one first. Okay, so over here in this step is where we define the forecast groups. And I'm gonna show you, not sure how many of you are familiar with Tableau Prep, but here is the formula for putting together the forecast groups. Really simple. We take the academic calendar, the academic group, or the what we call the faculty academic grouping. We combine it with the program that the student is in, kinesiology, mechanical engineering, the grant categorization, the tuition categorization, and the fee schedule. Really, it could be a lot more complicated, but it's really simple. So those 5 components make up the forecast group. And then you can see down below the values. These are the forecast groups. And where is the count? I just want to grab the count. It's over here. So let's widen this. Here's the forecast group. In this case, 281 count, 280 forecast groups here in this version of the model. And what we really like about Tableau Prep is it's a very visual tool. So you can see the results of your transformation right away. And so if you look at the various values here, you can see how the students are grouped. And in real time, you can change it. So if you believe that 280 groups are too many to keep track of, well, why don't we just concentrate on tuition groups, get rid of grants, save this. And in real time, you'll see that the 280 groups have now changed to 246. So in real time, you can see how the groupings are changing. And basically, I'll quickly show you that's useful.
Before you move on to the next step, Lenoy, how did you decide which variables to put into your forecast group?
That was by consultation with the budget and resource planning team. It went back and forth quite a few times. We knew that from a revenue projection point of view, we needed the grant information, the tuition information, and also the headcount. So that was the main driver. Obviously, Canadian versus international as well. What I think is important is this, from this point on, the forecast group is just a string, meaning no matter how you define the forecast group, the prototype works. So whether you make it more detailed or less detailed, the algorithm is designed to work with the groups that you give it to produce a forecast at the level that you specify.
Very cool, thank you. That was a question from one of our attendees here. I'm not that smart to ask those questions. That's above my pay grade.
Okay, so basically, you guys saw the Venn diagram before. This is where we implement that Venn diagram algorithm, combining the students in a previous term. Let's see if I can zoom in here. Oops. Scroll over to the right. Combining students in the previous term. Oh, come on, here we go. Let's see if I can show you more. There, previous and future S terms. So if you're in previous and you've got a matching record in the subsequent S term, transitions or transfers, if you came in a future S term and we can't find you in a previous S term, you're going to be an intake student, meaning new to the institution. So basically, we're using Tableau Prep to determine all the transitions and so on. And if I scroll far over to the right, let's see if I can find, let's see an example here. So in Tableau Prep, we calculate the transitions, and there are going to be a lot of zeros here. Let me see if I can find one particular group. Again, really like this tool for rapid prototyping. Sure, why not electrical engineering? So keep only. So looking at 4-month transitions. And then sometimes you get a lot of zeros in the matrices. They're differing values. So I'll show you the CSV file that's output, because as you saw for the example in mechanical engineering, a lot of the matrices are empty. But anyway, that's not too critical right now. The point is Tableau Prep is used to generate those percentages in the transition matrix. So that's a quick demo of Tableau Prep. So let me go back to.
We have another question that's related more to your model. Did you use any, or do you, I'm going to reword it a little bit and say, do you intend to, or are you currently using any benchmark models as a reference, like a univariate type of model, like ARIMA or exponential smoothing?
Yes, and I'm going to get to that soon. It will come up in the next couple slides.
Brilliant. Okay, great.
Okay, so I showed you how we create the transitions using Tableau Prep, and here's exponential smoothing. So when we're predicting future intakes, we use exponential smoothing. It's predicted using Python code. We're also experimenting, to be honest, with linear regression and simple averages, arithmetic integrated moving averages, and so on. So far, the linear regression is the simplest and it works best. And then, as I've said before, we predict enrollment using Python. We loop so that algorithm that I showed you with the transition matrices and the intakes, we implement it using Python. We put it in a loop and we spit it out. Okay, this is what the output looks like. The forecast group, 280, 480. Now I forget the number. The source of the intakes. So there are a couple different sources. You saw that we use exponential smoothing to calculate the intakes, but we also run a version of the forecast with faculty targets, and that's what we call V for vanilla. The projection on the output file, it can be new students, continuing students, students who came back after 4 months, as shown here. The S term is shown here. In this case, this is January 2022, that's May 2021. Historical period that was used, 5 years of data. The period we're forecasting, May 2021 to January 2026. The measure we're forecasting is headcount. The year level is, I've described that before, 1A, 1B, so on, and the measure. This output is generated 27 times because we're running things in parallel. So if you look at the bottom of the screen, we run it for headcount, FFTE, and WGU. Because one thing I didn't mention last time, the matrix algebra works whatever measure you put in it. So we don't have to do it with headcount or FFTE. We actually can do it with both. I mentioned that we do 3 historical bases, 1 year, 3 year, 5 years, and then we do 3 versions of intakes: vanilla, faculty targets, calculated intakes, exponential smoothing, linear regression, and we do a naive forecast as well. And then, if you can imagine, we can parse this output data or consolidate it to do flexible reporting. So if you need reporting at a faculty level, take the first component of art of the forecast group, arts. If you need program level reporting, psychology is that second level. If you need to group by grant and report, take the third component of the forecast group, so on and so forth. So you can do Canadian versus international reporting. If you take the semester, in this case, May 2021, you can roll that up very easily to academic, fiscal, or calendar years. You can roll the year levels up into first year versus upper year, academic versus work terms, and there's also a grouping of tuition fees. And in step 5 in the cube, we also have added in additional measures, so error measures as well, for QA and for testing. All right, so let's talk a little bit about Tableau Reports at the back end. So I'm running out of time here, but there are a few reports that I can show. So where is it here? Here we go. So let's start here. Erica, can you confirm for me that you can see the crosstab Tableau report?
Certainly can.
Okay. So hopefully it's easy to see. So on the left-hand side, those of you who are familiar with Tableau are all the measures and dimensions that you can report on. So here's an example of faculty there. That's the calculated field, but let's not focus there. And then various filters that you can put in. Although we can do a lot of really amazing reports in Tableau, because we're in the testing phase, we're focused right now on crosstab reports. And what I mean is comparing forecasted numbers versus actual numbers. So what you see here is an FTE forecast comparing actuals versus calculated for 9 semesters from fall 2017 until winter 2020. So here, this is international versus domestic students, FFTE numbers. I'm hoping you can see this, but basically the numbers are all very close, well within 5%. So for example, for the first semester, 4,300 was the actual. We forecasted 4,295. If you don't want to get lost in the weeds, we can just talk about totals. So in terms of Canadian totals, 70,000 versus 72,000. International total, 16,902 versus 16,231. That's the grand total over 9 semesters. No fee students, 604 was forecasted, 568. But again, remember, we're forecasting it by semester. And so you can also look at the totals by semester. So the actual was 5,450 FFTEs. We forecasted 5,367. And so on and so forth. You can see the numbers are all pretty good. Now you might say, this is amazing. This is well within your tolerances, 3%, 5%. So you can put it into production and we can start forecasting with 89,000. Well, it's not that simple because we tend to forecast conservatively. So the fact that this is within, let's say 1%, 2% over 3 years, it's actually still a concern because we prefer to under forecast. And so the question is, do you want to forecast 89 and come up short, or do you want to forecast 87 and then have a nice surprise later on? Here's another report. This one we're doing international versus domestic by faculty. It's the same layout again, simple crosstab report. The applied health services faculties, you can see numbers are very close. We can show it by engineering as well. And maybe these numbers, there's too much to take in here. It's the same breakdown. Maybe if I show you this is a better way to do it. So the blues are the actuals. Remember I said we're open year round. So September, fall semester, winter semester, spring. And then these are the matching forecasted numbers for the 9 semesters that are forecasted. So obviously you can see the results are really good. This is Tableau, so we can play with this 100 different ways. If you don't want to see all the faculties, you can focus on engineering. If you don't want to see 5 years of historical bases, but you want to see what it looked like over 3 years, you can do that as well. It's all dynamic. They're different periods. And I can drag and drop this 100 different ways, different measures, so on and so forth. So this is FFTE. This is head count, same histogram. Again, you can pick all the STEM faculties if that matters. Science, because the cube enables dynamic reporting. I'll stop there because I'm really out of time and there's probably a lot of questions. But basically, Tableau reports allow us to do flexible reporting at any level. Why are we in testing? Because there are literally hundreds of data points to check. So Erica, I'm going to stop here because I see we're at 2:52 and I did want to leave time for questions at the end.
Yep, and the problem is as soon as I switch my screens, I lose the questions. So we've answered most of them in flight, which is awesome. I'm just going to have a look and see if there's, oh, we got another one. Hang on, it's a lot of words. I have to make my little chat here bigger. All right. You mentioned that this is currently a manual process. How often do you pull data from PeopleSoft and run your other calculations, Python, etc.? Then refresh the data underlying the Tableau workbook. Wondering if you do this annually using November 1st enrollment counts, quarterly.
We do it every semester. So let me show this slide. If I show this slide, it will make more sense. So I'm trying to get to my next slide here. All right, there we go. There. What we're doing is a rolling forecast. The data I just showed you is highlighted in the snapshot from Excel. So we have forecasted 9 future semesters using 15 historical actuals data. So what you're seeing here is a stepwise progression. For every semester where we have a new actuals, we then forecast 15 semesters into the future.
So it's like a rolling 15.
It's a rolling forecast. And then we archive all the historical data so you can compare this semester's forecast from 3 years ago versus this semester's forecast from 2 years ago.
Yeah. Here's a question that we get a lot on the financial budgeting and planning side, but I'm interested from an advanced analytics point of view, how you're handling this. And that is, how do you forecast a new program that doesn't have any historical data, like a totally new program? How does the chair take this, input their intake, and then split the enrollment projection for the next few years?
Right. So what we do is there's code in the Python. I don't think I have time to show you, but there's code in the Python that basically says, hey, were you able to find any transitions for this particular grouping? In our case, let's use architectural engineering, which is a new program. If no, then it allows you to say, what transitions would you like to use with this program? What program is close enough to it that you could use the transition? So architectural engineering, hey, I'll use architecture because that's been around for decades, right? So that's how we handle new programs, by using matching program transitions until there's enough history that it can use its own data.
Excellent. Almost like a weighted look at it.
Many
Right.
programs are similar. So electrical is similar to computer engineering. Mechanical engineering is similar to mechatronics engineering. So if you don't have mechatronics data, you can override the transitions with mechanical data until some point in the future where you have
Yeah.
enough historical.
Right, right, of course. Okay, so two questions in this one. What does WGU stand for? And the second one
Um,
was, what model did you use for the new intakes forecast?
right. So WGU is weighted grant units, and I'm not an expert on it, but basically it's the units that are applied to each type of program, so kinesiology and mechanical engineering, French, and different programs have different weights, and the value of those weights is what determines your provincial grants.
Got it. Okay. And then how did you model the new intakes?
Um, New intakes, we do, well, we have two sources, right? Because we can do it by using the faculty targets, or so we've used the faculty targets. When we were using the faculty targets, the numbers weren't quite what we expected them to be. And so we said, maybe there's an issue with the faculty targets. So we said, what if we used historical intake patterns to predict future intakes? So very simply, we used linear regression, and we found that in many cases, what was predicted by linear regression for intakes was more accurate than what the faculty gave us as targets. And that's because the target setting process is sometimes political, meaning a faculty member may say, oh, we are expecting 50 international students this year. But history says you've never had more than 10. So a calculated intakes would be, we expect 10, because 10 is what you've had for the last 5 years. But 50 could be right in theory if there's a big recruitment push on by that faculty for international students. So we use both in the forecast model so they can compare results from either or.
Okay, very cool. Another question here. I saw you didn't separate full-time, part-time. How much, I can't see the end of it. Oh, how much do you think that will impact?
We, the vast majority of students at University of Waterloo are full-time. If we wanted to do part-time students, in a sense, when we do an FTE forecast, full-time equivalent, essentially that covers full and part-time, right? So a student who takes 3 courses is 0.6. A student who takes a full course load would be 1.0. So FTE essentially covers part-time students. But if we wanted to really break out part-time students, we would include a categorization in the forecast grouping. So along with faculty and all those categories, would also include a part-time, full-time grouping. And then you would double the number of forecast groups, and the forecast would run for 1 day instead of half a day and all that kind of stuff. So it is possible for us to do it, but we don't think it's valuable at this time.
Yeah, yeah, that makes sense. Okay. Could you please speak a bit about what you now want to do with your forecasted data? Like, how are you using this? Or I know we're still again prototype, but how are we anticipating using this data?
So really, right now in the short term, the BURP team, Budget Resource and Planning team, is going to test every data point to make sure that it's producing the results that they expect. And then we will take the output from the enrollment forecast to build a revenue model. So we'll be able to model tuition revenues by using the FTE forecast, model grant revenue by using the WGU forecast, and model co-op revenues by using the headcount forecast. Put it all together in a crazy spreadsheet, and you should be able to forecast revenues at any level: faculty, program, department, Canadian versus international. That's the medium-term goal. Longer-term goal: share this data with the campus, allow, make use of Tableau's web editing and web reporting to do dynamic reporting, see the data any which way you want to see it. Whichever way you look at it, the data will reconcile.
Right. Okay, so we still have a few more if you're okay to keep going for a minute here.
Yeah, I apologize. It's quite
No,
a
no, it's a lot. And actually I thought you did a really good job of keeping it very succinct. So the questions are really relevant. So I don't want to cut it short and leave someone hanging. Not sure how long you've been doing this, but how accurate is it so far? Are you getting that within 5%? It sounded like you were, but I want to confirm before I answer on your behalf.
Yes, easily within 5%. Maybe if I show here are the numbers. So let's go here. So this is a headcount forecast. The actual number in fall 2017 was 20,454. We forecast with the model 20,337. In the spring of 2019, the actual number was 14,809. We forecast 14,229. Here I've only, I could do all the faculties, I guess. It's dynamic reporting. So winter of 2020, just before COVID hit, 33,000 of forecast was the actual headcount across the institution. We forecasted 32,835. So we're well within the boundaries, and that's headcount. We could do the same for FTE as well. The FTE forecasted numbers are slightly higher, 2546 versus 2492. It's very accurate, but how to say it? We're not just checking the accuracy at the institution level. We're checking it at the faculty level. We're checking it at the program level as well. So there's just a lot of data points to go through.
Right.
But
okay.
So far it's been very encouraging.
Very, very. That's great for a predictive model, honestly. So we have a few more. So we're going to try and talk fast and keep it brief. Any idea how this is? I'm sure on everybody's mind how COVID will impact your calculations.
So it will impact the calculations, but let me see if I can how to say it. Two different ways to answer that. I was actually hoping to produce a report that showed the reporting across COVID, but I didn't complete it in time because most of our focus has been on checking against history to see if we're close. But two things to keep in mind. One is because of the model, let's see if I can bring up this algorithm again from current slide. So if I remind you of the algorithm, you'll see that this Markov model allows us to make adjustments for either the intakes next semester or the semester after that, or the semester after that, or the semester after that, and the same for transfers. So you remember I used the analogy of a car with a manual transmission. You have that much more control versus doing an automatic. So that's the first thing I want to say. In this case, the fact that the intakes for COVID may be different, you can override them, or you can just change the intakes in future semesters. So that's really quick overview. But the second thing I want to show you is this slide, the rolling forecast. Where is it? This one. Okay. So because you're doing a rolling forecast, so across the top, you've got calendar years, right? So 2020 was the COVID year. So if you think of these 3 semesters here, the first time we forecasted for that period was with this running forecast. But then because you're doing a stepwise forecast, eventually you're getting closer and closer data, closer and closer to the COVID numbers. And what you'll find is the forecast is essentially self-correcting, meaning once you have actuals data in the system, like here for winter 2020, it uses that actuals data for the forecast for the next 9 semesters. So it actually accommodates COVID really well. And what I'll probably do is when I share the slides, I'll show one of my newer reports that spans the COVID year, so you can see what the hiccup was and how the forecast handled it. I'm trying to answer all the questions really quickly. I'm good.
Yeah, that one was a tough one. Sorry.
Another half
okay.
an hour, but that's the quickest way I can answer it.
Yeah, last question, I promise, because they're still coming in, which is awesome.
Take your time. I'm not. I have no meeting scheduled for the rest of the day, so I'm good to answer the questions.
what is the range of the percentage difference between the actual and predicted, and how is it related to the size of enrollment in the predicted groups? Individual program versus school versus institution. I know we've seen in NUCOMP's practice, if we don't have enough data points, it skews the prediction. So I don't know if that's sort of what Luke is getting at, if that's a problem.
Right. So the idea here is, I think I should show this. Where are you? This one. So I think what the question is asking is, how did we decide at what level to define the forecast groups? So the way I thought about it, the way we thought about it was, what's the level at which you really want to be accurate? And in this case, we have a categorization called tuition fee group. And it really represents how fees are grouped across the institution. So engineering essentially has one fee group because all engineering programs are co-op, all engineering programs are honors, right? So there's one fee group for all of engineering essentially. But when you get to programs like math, where they're regular and co-op students, so you could have computer science regular students, computer science co-op students, really there are more tuition groups. So, but these, the 400 or so forecast groups that we have, and just a sample list here, roll up into 50 tuition fee groups. Once it was determined that the 50 fee groups is where we want to be accurate, the goal was to forecast at a level below that. And if the level below that was accurate, then when you roll up the values from 400 to 50, for example, you're going to be accurate. In other words, if you're within 3% at the faculty level, you will be within 3% at the institution level. So when we chose this level, the institution forecast is within 3%, the faculty forecasts are within 3%. The fee schedules, those fee categories, they vary by faculty, and there is still some investigation as to which ones are close and which ones are far off. And we're still working through that. And that's why I wanted to say at the start, we're still testing some of the data points. But at an institutional level and faculty level, we're well within tolerance.
Great. Okay. That actually makes a lot of sense. We are losing a few people. I did just want to do a shameless plug for Tableau conference. It's happening next week. So if you are a Tableau user or would like to be a Tableau user, I highly recommend this event. It's a great, energetic event, and it's all online. And the best part is it involves my favorite four-letter F word. It's free. So there you go. No charge, no travel. So I'm going to flip back to the questions here. I've got another one. How are you handling targets that are set based on academic year versus fiscal or budget calculations?
Targets are set by semester, so we don't have to worry about academic versus fiscal year. I can show you an example of the spreadsheet, but basically the target data we receive is by semester, so we're able to pull it into the model by semester and then roll it up to academic, fiscal, or calendar.
Right. So if a user was given a target, which I don't know if that even makes sense, they could easily just divide by semester, yeah?
They could. It's not a concern for us at this time. Of course, the vast majority of our intakes come in the fall semester. So if they're giving us data by academic year, it's usually the fall semester. Makes
sense. Okay. Every time I answer one, it takes me to the back of the list. Any good papers on how to call Python from Tableau? No, you need your friendly neighborhood NUCOMP people. No, yeah. I don't know if that's basically how we did it, right, Lenoy?
Yeah, so we as we're looking into automation, what we're looking to do is wrap the Python programs in Tableau Prep flows and then run them on the server by running the prep flow.
Yeah. So Alex, maybe you can remind me to try and find something that we can send out. Maybe we can get somebody to write a blog post. Wouldn't that be nice?
If you're seeing my screen, going back to the question about tuition fee groups, here are some of the groups here and the actuals versus what we calculated. I'll just leave it up on the screen for you to see the good, the bad, and the ugly.
That's great. Thank you. how do you account for any additional inputs such as divisions, goal, and strategies, or in some cases maybe even marketing? I just made up that
That's
last one. The question is about the
that's
goals and
reflected in
strategies.
the targets. The targets that we get from the faculties reflect all of that marketing and all that push. It's what the faculties tell us to put into the forecast. When we also run the parallel forecast with the calculated numbers, it's solely based on history. So you can actually compare the two numbers to see, in this case, for example, I'll show you very quickly. Here you've got actual versus calculated forecast for FTE. I'm just going to drag in the what we call the vanilla. And that is the faculty target. So now you see for any given grouping, what the actual number was, 211, what we calculated it to be, and what if we use the faculty targets, what the number was. So all the numbers are up there, and you can compare it. If you look at the totals on the right, you can see, for example, for the Applied Health Studies faculty, the actual number was 7,100 over 9 semesters. We calculated 6,500. If we use the targets, we'd have gotten 6,200.
Interesting. Very, very interesting. I think we've actually exhausted the questions. So great job, Lenoy. Like, amazing. Some really great feedback in the chat that I'll send you as well. I cannot, on behalf of myself at NewComp and so the NewComp team and the Tableau team, are so very grateful for your generosity of time and spirit and your enthusiasm, because this is very, very, very cool. And of course, the question I warned you that was coming is, can we get the presentation? So yes, everything except the demo.
Yes, yeah, I'll send the presentation. There'll be some extra slides at the end of it that might be helpful. And I'll send along some screen reports as well, just so you can see what the data looks like and that we're testing right now.
Great, great. That sounds great. Thank you so much again. And we will follow up with everybody for our next webinar. So please don't hesitate to hit us up and get on the mailing list for the next webinars. Tell your friends, tell your family, tell the whole bunch. Have a great day, and I wish you be well and good luck.